Hi, and welcome to minijack. As you might notice, this is a little bit different than the usual. Sometimes I feel like I want to take a break from the cold hard truth of hardware, I guess. So I do some programming, and in this case I am doing something about tuning systems today. That's what we'll see. And I always like to stay close to the metal when programming, so I'm using C, which is not the closest you can be. Could still write assembly, but I'd like to be a little bit comfortable writing code, so that's why I go with C, and it's also a little bit more portable if I want to take it out of the computer and maybe into an Eurorack module, or just a prototype on even an Arduino or any other microcontroller, or on a Bella or a Raspberry Pi, or any other, let's say, embedded device out of a traditional computer with a screen. And so today we will be exploring the variations on the 12 equal temperament. So let me know down in the comments if you like this type of content, as I would love to mix hardware building and software building and writing in this channel, as I think it's quite interesting. The software space is very interesting. Let me know. So let's get into it. We are exploring the 12 equal temperament and its variations. So what is a 12 equal temperament? It's the kind of the basic building block of music. And let's start from this one, which is the 12 equal temperament, which is the base of classical and, let's say, traditional Western music. So it means that each octave is divided into 12 semitones. They're known as A, B, C, D, E, F, G, with all the hashes. And this is one of the ways you can do it, of course. And the equal temperament, the equal means the intervals are all the same size on a logarithmic scale. So what we are seeing here, they look like they are the same size, but they're not actually. They are in a logarithmic scale, but that's how our ears work for physical reasons. The shape of our ears and all the biological things involved in the sense of hearing. But of course, we can decide always to stay in the constraint of equally divided, in a logarithmic sense, octave. We can decide to divide it in fewer parts, so as a 7th or a 5th, but of course we can go 2th, which wouldn't make sense because you would have only 2 notes, but we'll see that as well. And you can also have more intervals in the octave. That's what is maybe sometimes called microtonal, because it brings out some subtleties in the frequencies that we don't usually hear in traditional music. We just like to step from here to here to here. We with a 12th det we will never hear any of the frequencies that lay inside here, only this one, this one, this one, and this one. But for example, with a 24th det, which is exactly the double, there will be an extra note between each traditional 12th det note. So for example, I chose Popcorn as a song to demonstrate that, because it's a very well-known song with a simple melody, and especially it's all 8th notes, so it's easier to focus on the tuning while listening. No weird rhythms going on. I mean, I like weird rhythms, but not today. So for example, this is the regular song. So we can see here that we have 12 intervals, and also the octave multiplier means by which factor we are multiplying our frequency to get the next octave. In all of these equal temperament things, there are two assumptions. All intervals are equal, and stepping an octave means doubling the frequency, so it's ×2. And in my little program, I also decided I could easily change the number by which multiply with each octave step. So that's an extra thing that will technically go outside of the 12 of the equal temperament standard. Yeah, standards. So this is the regular one, and for example, the 24th det that we were mentioning before, it's used in some parts of Arabic music. So for example, we can translate this popcorn song with 24 intervals. And you hear it's you can still recognize it's the melody, but it sounds very much different. I think it's interesting. It sounds good in its own melody. You can also lower the octave or pitch it up. Maybe this one sounds a little bit better if it's lower. And for example, in this configuration, I will have the same melody, the popcorn melody. Maybe the notes, we can visualize the melody as like the player jumping between intervals, just only on the stripes, you know. And if I have 24 of these steps, the same melody will be stepping in less space, exactly half. So if a melody spans in 12th det like this, it will span like this. And something we can do to make it resemble more the original is multiply by the double amount the octave. So I can multiply by 4 the octave. So that's a bit into uncanny valley situation where yeah, apart from this big octave step, it resembles very much the original, but there's something very weird and off going on. And that's interesting because from a mathematical point of view, we doubled everything. We can even go farther, I think, with 48 intervals and 8 times the octave. You have very low lows and very high highs. But yeah, and that's the original one. Just for comparison, I will sometimes put the original one. and oh, no, I closed it. And for example, we can also see other things. So maybe I just will. This is the melody. I will just have a quick look at the code. So basically, the equal temperament system is a system that makes a frequency from some data. So that's what I have in this function here. It's called frequency maker. So it will output a frequency given some data, and this data is a tuning system, an octave shift, a scale, and an interval on this scale. In this case, as a scale, I'm using a chromatic scale, so I have all 12 intervals, and so I am basically building the frequency starting from the tuning system, and the tuning system is this thing which consists in a root frequency, which is usually the A frequency. In the classical music it's 440 Hertz, 440 Hertz, and an octave multiplier, which we just discussed. So it's the number by which you multiply frequency to have the same note on the next octave, or divide by the same number to have the same note on a lower octave. And how many intervals is the scale is made of, and the octave is divided into. And as you can see, the intervals number is an integral, because it doesn't really make sense to divide in a non-integer number of intervals, of course. But I can multiply for any number to obtain the octave, and we will see. Maybe we can just have a look. So this is the regular melody, but for example, instead of multiplying by 2, I can multiply by 1.5. So basically now the melody will be more contained, because it's like each octave is smaller, so all the sounds gets compressed. And for example, like 1.5 would be like minus a fourth, like right about here. So every note that jumps out of this boundary will not be here, but will be on the next octave. For example, as we took out a fourth of the multiplier, we can add a fourth in the intervals. So a fourth of 12 is 3, so that will make 15. Now it sounds kind of more natural, because the two numbers are kind of in sync now. Or we can also do it with a quarter, that will make 18. Oh yeah, but I guess I should make it 1.75. Yeah, that's right. And in general, it's yeah. Sometimes I'm just letting the music play, so you can hear. Sometimes with the I can bring back the default tuning. And I think it's quite interesting to have multiples in the octave multiplier and interval divider. Like for example, I can multiply by 3. It's also interesting, just multiplying by 3 instead of 2 and leaving the intervals as they are. We can also do the opposite, for example, halving the intervals. Nice, very nice. And for example, I can multiply the octave by 3 and have 18 intervals. They're multiples and they behave. Now sometimes it gets stuck. Yeah, my code is not perfect, I have to say. It sounds kind of decent, not too weird. That's also quite interesting. We might also want to have, oh wow, all prime numbers. For example, 5 is already a prime number. We can also have maybe 7 intervals. So it's less easy for them to catch up, and the melody is more varied. By the way, that's this is the melody. This is the list of notes I'm using. And yeah, I think it's very interesting, and of course this is not the only way to divide octaves. For example, there is another system that is called EDO, or we have like the perfect, how is that called? The just interval ratios, which are shown also in this table here. But yeah, I think it's interesting to just explore one system. As you know, I like minimalism in the sense of taking a small set of things and dissecting all the ways you can come up with interesting things just with the variations in those settings. Another very interesting thing, in my opinion, is that the octave multiplier doesn't have to be more than 1. So if it's smaller than 1, the frequency will not be higher when you go on a higher octave. It will be lower. So you can kind of invert melodies in this way. So let's hear it. So this is the default melody. If, for example, I do it with 0.5, which will be, instead of multiplying by 2, will be dividing by 2, because multiplying by 0.5 is the same. I think that's very fun. This is a funny sounding music. Of course, if I go up with the octave, I'm actually, if I go down, I'm actually going up. So I have to, with X, I usually go up with the octaves. But here and going down because I'm multiplying for 0.5. That's even more funny like that. And another thing I can do is to, as I'm halving the frequency on each octave step, I can also decide to have half the interval span, that would be 6. It's very fun indeed. Let's go with 7. Let's go crazy. Prime numbers. Subsonic octaves like this, because with 7, yeah, it's just too much. It's 5. Just a dub of the default tuning, just to remember where we are coming from, kind of. So let's try something more extreme now, like let's start from 6 intervals. Down 5. So my melody is smaller and smaller. Oh no, again. We were saying intervals 6, intervals 5 is getting smaller and smaller and smaller. So now it's about that small. So when the melody comes here, yeah, did you hear that? It has to jump to the next octave, and in our case we're just doing the regular octave thing multiplied by 2. I can make it even smaller. You hear the fewer the intervals in each octave, the wider the octave span becomes, using the same melody, the same starting point. Of course, I guess somebody composing in this kind of system wouldn't compose the same way we compose with 12 intervals. We can try to invert that now. And at this point, the original melody is a little bit lost, I have to say. Let's go back to doubling the octave, the frequency for the octave. We were at 4, let's try 3. Let's try like octave 1.5, so we have a little bit smaller frequency span on each octave, as we are traversing so many octaves now because of the low interval count. Oh, and by the way, this image is from Wikipedia. Yeah. Don't arrest me. It's quite interesting. Maybe on a lower octave. Oh, by the way, I also put some little filter on the melody. So the second part is more bright, kind of, just to, there's a little homage to the original Moog version of the song, which I guess is not the original, maybe, yeah, most famous one. And yeah, we can also, we had 3, we can have 2. That's quite crazy. Yes, not even that melody anymore. It starts to be kind of painful. And the original melody spans on 3 octaves. There's a main octave and something on higher and something on a lower. But here, wow. Yeah, halving the volume. But yeah, again, the original. So yeah, I guess that's it. I will put the code somewhere, maybe Pastebin or something, so you can experiment and play as you want. I built also this little kind of live coding, or let's call it live tuning environment, where you have several commands to change the octave, go back to the default tuning, and of course change the multiplier and the intervals. And yeah, you can also play with the math of the ADSR, which is actually an ASR envelope, and I will do some playing now. So yeah, if you like this video, hit the like button. If you're not already, consider subscribing to the channel and stay tuned for more videos.